5,000 years ago, along the fertile banks of the Nile, a civilization emerged whose achievements would resonate across millennia, leaving monuments and artifacts that still evoke awe, curiosity, and wonder. These were not just constructions of stone. They were manifestations of human ingenuity, determination, and mastery over the natural world. From colossal statues that towered over cities to pyramids whose sheer scale defied comprehension, ancient Egypt showcased a technological sophistication that continues to challenge historians, engineers, and archaeologists alike. Imagine standing before a statue of Ramses II, a figure over 20 meters tall, carved with precision so exact that the contours of the face, the lines of the eyes, and the expression of divine authority seem almost alive. Now imagine the process that brought such a figure into being. Enormous granite blocks quarried hundreds of kilometers away, transported across deserts and along the Nile, then meticulously shaped, polished, and positioned using only tools available in an era before steel, electricity, or cranes. Each chisel mark, each polished surface, each perfectly aligned joint represents not only skill, but a profound understanding of materials, mechanics, and geometry. The Egyptians achieved what modern observers might call impossible. Their temples were built with blocks weighing tens of tons, yet placed with such precision that centuries of erosion and seismic activity barely disrupted their alignment. Pyramids, their smooth limestone casing glinting in the sun, were aligned with the cardinal points with remarkable accuracy. Obelisks soared skyward, monolithic and precise, their tips and bases aligned to millimeters. The very act of planning, transporting, and erecting these structures required more than manpower. It demanded knowledge, foresight, and innovative techniques that were honed over generations. This civilization understood not just how to manipulate stone, but how to manipulate natural forces. They harnessed the seasonal floods of the Nile to facilitate transportation. They observed the behavior of sand, water, and friction to move enormous sledges across deserts. They experimented with levers, ramps, and pulleys, developing methods to lift blocks far beyond what raw human strength alone could achieve. Even in an era without formal physics, they intuitively applied principles that would later be articulated by scientists: force distribution, leverage, load management, and material resistance. Yet their technology was inseparable from their culture. In ancient Egypt, engineering was never purely practical. It was spiritual, political, and social. Colossal statues were embodiments of divine authority. Temples aligned with the stars were not only architectural marvels, but celestial instruments connecting the mortal realm to the cosmos. Pyramids were tombs and astronomical markers, designed to preserve the pharaoh's soul and align with celestial events. In this way, technology and belief were interwoven. The act of building was itself an expression of devotion, a physical manifestation of societal order, and a reflection of the pharaoh's power. The question naturally arises: how did they do it? What knowledge, seemingly lost with time, allowed them to carve, move, and erect massive stones with such precision? While some scholars have attempted to explain these feats using modern engineering analogies, it is essential to appreciate that the Egyptians' methods were products of centuries of accumulated experience, observation, and experimentation. They developed techniques tailored to the specific properties of each material: granite, limestone, sandstone, understanding how to quarry, shape, transport, and position them efficiently. Copper chisels, wooden mallets, dolerite pounders, ropes, sledges, and ramps formed a technological toolkit that, when wielded with skill, produced results that remain breathtaking today. Consider the Great Pyramid of Giza. Constructed over 20 years, it required approximately 2.3 million blocks of stone. These were quarried, transported, and placed with extraordinary precision, forming a monument that has stood for over 4,500 years. Modern engineers marvel at the logistics alone, the coordination of labor, the transport of massive stones, and the alignment of the structure to the cardinal points, all achieved without cranes, trucks, or digital instruments. Experimental archaeology has demonstrated that many of the proposed methods are feasible, though the sheer scale and organization required remain astonishing. The mystery deepens when we examine colossal statues. Pharaohs such as Ramses II and Amenhotep III commissioned figures that weighed hundreds of tons, carved from single blocks of granite or sandstone. How were these blocks quarried, transported over uneven terrain, and positioned upright with such stability? Scholars suggest a combination of ramps, levers, and sledges, yet the precise methods remain partially speculative, preserved only in tool marks, surviving sketches, and the enduring monuments themselves. What is undeniable is that the Egyptians combined observation, experimentation, and practical knowledge to solve engineering challenges that still challenge modern minds. Even the smallest details reveal their mastery. The angles of cuts, the smoothness of polished surfaces, and the precision with which blocks fit together testify to a civilization that understood both the macro and micro aspects of construction. They studied the behavior of materials under load, the forces generated by moving sledges over sand, and the interactions between stone and tools. They experimented with water lubrication, sand packing, and manpower distribution to optimize results. Each successful construction was the culmination of careful trial, observation, and adjustment, a continuous refinement of methods passed down through generations. Beyond the physical achievements, there is also the philosophical dimension. The Egyptians viewed their technology as a way to bridge the mortal and divine realms. The monuments they created were not only practical expressions of authority or engineering skill, but they were manifestations of cosmic order. Temples aligned with celestial bodies, statues facing the rising sun, and pyramids oriented to the stars reflected a worldview in which technology, astronomy, religion, and governance were inseparable. Engineering was a form of devotion, and precision was a reflection of the harmony between human effort and the universe. In studying these ancient feats today, we gain more than insight into stone and tools. We gain insight into a civilization that observed nature meticulously, experimented methodically, and applied knowledge with extraordinary foresight. The Egyptians remind us that technology is not merely a function of available tools, but of ingenuity, organization, and the capacity to imagine solutions beyond conventional limits. Their monuments endure as silent witnesses to human potential, challenging us to understand how knowledge, culture, and ambition combine to create works that still command wonder. Segment 1, therefore, is not merely an introduction, it is an invitation. An invitation to explore the full depth of Egyptian ingenuity, to question the limits of ancient technology, and to witness how a civilization without modern machinery transformed stone, sand, and manpower into enduring symbols of power, faith, and intellect. Each statue, each pyramid, and each temple is more than a construction. It is a testament to human curiosity, perseverance, and the relentless drive to understand and master the natural world. To comprehend the extraordinary technological achievements of ancient Egypt, one must first understand the civilization that demanded them. Technology does not exist in a vacuum, and in Egypt, it was inseparable from social order, religious belief, and political authority. At the center of this society stood the pharaoh, the living embodiment of divine power, a ruler whose word shaped both life and afterlife. The pharaoh's authority was absolute, but it depended on a sophisticated bureaucracy, a well-structured labor system, and an understanding of logistics that, in many ways, rivaled the complexities of modern project management. During the Old Kingdom, roughly 2700 to 2200 BCE, Egypt reached a period of political stability and prosperity that enabled the commissioning of monumental construction projects. It was a time when pharaohs, seeking to eternalize their rule, embarked upon ambitious endeavors that combined utility, devotion, and spectacle. The step pyramid of Djoser at Saqqara, designed by the architect Imhotep, represents the beginning of this architectural revolution. Unlike earlier burial structures, which were simple mastabas, the step pyramid demonstrated a sophisticated understanding of geometry, load distribution, and symbolic representation. It was a structure designed to convey authority, permanence, and connection to the divine, in a model for all subsequent monumental architecture. As Egypt transitioned into the Middle Kingdom, from approximately 2050 to 1710 BCE, there was a marked evolution in both artistic and technological sophistication. Pharaohs commissioned temples and statues that were not only large and imposing, but also intricate in detail and precise in alignment. The obelisks of Heliopolis, rising from the desert floor like stone spires reaching toward the heavens, exemplify this era's combination of aesthetic elegance and engineering mastery. These monuments were carefully quarried, transported, and erected with a level of accuracy that suggested meticulous planning and mathematical understanding, yet achieved without the tools or machinery we might consider essential today. The ability to undertake such colossal projects was rooted in the social and economic structure of Egyptian society. The Nile River was not merely a geographic feature, it was the lifeblood of the civilization. Its annual floods deposited fertile silt, supporting a highly productive agricultural system that freed a portion of the population from subsistence farming. These individuals could then dedicate their labor to construction projects, crafts, and administration. This surplus allowed pharaohs to marshal tens of thousands of workers, organized into teams that understood their specific roles from quarrying and transporting stone to carving, polishing, and erecting massive statues. Skilled artisans were central to the technological achievements of the era. Knowledge of stone properties, tool usage, and measurement techniques was passed down through generations, often within guild-like systems of training. These artisans understood the hardness, grain, and fracture patterns of limestone, sandstone, and granite. They knew how to exploit natural properties to achieve desired shapes and finishes. Copper chisels, wooden mallets, and dolerite pounders formed the basic toolkit, yet the mastery lay not in the tools themselves, but in their application. Repetition, observation, and empirical experimentation allowed them to refine techniques to a level that enabled remarkable feats of precision. Egyptian technology also relied heavily on careful observation and adaptation to environmental conditions. The transportation of massive stones from distant quarries to construction sites involved sophisticated logistical planning. Stones quarried in Aswan, hundreds of kilometers upriver, were transported via the Nile using barges, rafts, and channels engineered to accommodate their weight. Once on land, sledges were employed, sometimes lubricated with water to reduce friction on sand, a technique documented in ancient reliefs and confirmed by modern experimental archaeology. This integration of natural resources, human labor, and engineering insight reflects a civilization that saw the landscape not as an obstacle, but as a system to be understood and utilized. Monumental constructions were rarely undertaken for mere vanity. Each statue, pyramid, and temple had profound symbolic and religious significance. Colossal statues immortalized pharaohs as divine beings, projecting authority over subjects and eternity alike. Temples, aligned with celestial events, functioned as instruments of cosmic order, bridging human and divine realms. The alignment of pyramids with stars or cardinal points was not arbitrary. It reflected a worldview in which astronomy, religion, and engineering were intertwined. This synthesis of technology and belief demonstrates that Egyptian engineering was never divorced from culture. The act of building was both practical and spiritual, a physical manifestation of societal values and cosmic understanding. Consider the Great Pyramid of Giza, a structure that epitomizes the convergence of social, religious, and technological factors. Comprising approximately 2.3 million stone blocks, each weighing several tons, its construction required an immense labor force, organized into highly disciplined teams with specialized roles. Yet beyond manpower, it demanded knowledge, the alignment of the pyramid to true north, the leveling of the base over a large expanse of desert, and the precise positioning of blocks to ensure structural stability for millennia. Experimental archaeology has shown that with careful planning and coordination, these feats were achievable using simple tools and human labor, but the scale of organization and foresight required remains staggering. The pharaoh's role in these projects was both political and religious. By commissioning monumental works, the ruler reinforced authority, showcased divine favor, and legitimized the state's social hierarchy. Each construction project was an act of centralized coordination, involving administrators, scribes, engineers, and artisans working in concert. The Egyptian state acted as both a patron and an organizer, channeling resources and labor in ways that reflect a sophisticated understanding of governance and logistics. Monumental construction was thus as much a political instrument as a technological achievement, and it required a society capable of sustaining such efforts over decades or even generations. Religion, in particular, infused every aspect of Egyptian technological ambition. Structures were oriented and designed to honor gods, maintain cosmic harmony, and facilitate the pharaoh's journey into the afterlife. The physical and spiritual realms were not distinct. Engineering solutions were conceived with the understanding that they served both earthly and divine purposes. For instance, the alignment of temple columns or the proportions of a statue might correspond to cosmological principles, ensuring that construction was in harmony with both human perception and celestial order. Technology, in this context, was not merely functional, it was sacred. Furthermore, Egyptian innovation was cumulative. Knowledge of quarrying, carving, transport, and construction was refined over centuries. Each generation built upon the successes and lessons of the previous, gradually developing techniques that enabled increasingly ambitious projects. This cumulative knowledge explains how methods for moving multi-ton stones, carving intricate reliefs, and erecting massive statues could be systematized and replicated, creating a technological tradition that was uniquely Egyptian. The interplay between labor, tools, observation, and religious purpose is evident in surviving monuments. Quarry marks reveal the types of tools used, the number of laborers required, and even hint at scheduling based on the Nile's seasonal cycles. Reliefs depict workers hauling stone, lubricating sledges, and coordinating efforts under the supervision of overseers. These records confirm that Egypt's technological achievements were the product of human ingenuity applied within a highly organized social and religious framework. Finally, the historical context reminds us that Egyptian technology was not isolated. While other civilizations achieved remarkable feats, Mesopotamia's ziggurats, the Indus Valley's urban planning, the integration of religion, governance, and engineering in Egypt created monuments of enduring scale, precision, and symbolic meaning. Egyptian advanced technology was thus a reflection of a civilization in which knowledge, labor, and belief converged to transform vision into reality. In examining this context, we understand that the monuments we see today are not only architectural wonders, they are the product of a society that harmonized human capability with cultural vision. Each pyramid, temple, and statue embodies a complex interplay of administrative skill, technological understanding, religious devotion, and social cohesion. Ancient Egyptian technology was, in essence, civilization itself, ordered, purposeful, and designed to endure. By situating their engineering achievements within the broader historical, cultural, and spiritual framework, we can begin to appreciate the full scope of what they accomplished and why their legacy continues to captivate the modern world. The achievements of ancient Egypt, from the soaring pyramids to colossal statues, were not merely feats of labor or organization. They were the direct result of an intimate understanding of materials and the innovative use of tools honed over centuries. To appreciate the sophistication of Egyptian technology, one must begin with the stones themselves, the fundamental building blocks of their civilization. The Egyptians primarily worked with three types of stone: limestone, sandstone, and granite. Each required distinct techniques, knowledge, and skill, and the choice of material was never arbitrary. Limestone, abundant along the Nile, was the backbone of Egyptian construction. Its relative softness allowed it to be quarried and shaped more easily than other stones, making it ideal for pyramids' inner cores, walls, and smaller statues. Yet even limestone posed challenges. Egyptian artisans had to understand its fracture patterns, grain, and susceptibility to erosion. Quarrying limestone required precise planning, determining where to extract blocks without compromising the surrounding material, estimating the size needed, and shaping them with care. Copper chisels, hardened through repeated hammering, were the primary tools used to carve limestone. Though soft compared to steel, these chisels, combined with abrasives like sand, allowed skilled artisans to achieve remarkably smooth surfaces and intricate designs. Sandstone, a harder and denser material, was used for certain temples and statues, particularly where durability was required. Sandstone quarries, often located in Upper Egypt, provided material that could withstand weathering and time. Working with sandstone required greater force and patience. Chisels and pounders had to be wielded with precision, and artisans had to constantly assess the stone for natural flaws that could compromise the structure. Sandstone's toughness demanded teamwork, as blocks were shaped, lifted, and transported by large crews, often coordinated by overseers who ensured efficiency and safety. Granite, quarried primarily in Aswan, represented the pinnacle of Egyptian material mastery. Its density and hardness are far greater than limestone or sandstone, making it incredibly difficult to carve. Yet it was prized for colossal statues, obelisks, and other monuments meant to endure for millennia. Granite was both a practical and symbolic choice. Its durability ensured longevity, while its imposing presence conveyed power and authority. Working with granite required innovative techniques. Copper chisels alone could not cut through its hardness. Instead, artisans relied on pounding with dolerite, a dense, volcanic stone, to fracture the rock along natural grain lines. Sand, water, and patience were essential to polishing surfaces and achieving precision. This process, repeated hundreds or thousands of times for each block, illustrates the Egyptians' understanding of the physical properties of stone and the limits of human labor. Tools, though simple in appearance, were applied with extraordinary sophistication. Copper chisels, wooden mallets, dolerite pounders, and stone hammers formed the foundation of Egyptian technology. But mastery lay in technique, timing, and coordination. Craftsmen developed methods to sharpen tools, adjust striking angles, and apply consistent force, all while monitoring the stone's response. Wooden sledges transported quarried blocks, often over sand, with teams strategically reducing friction by pouring water or other lubricants beneath the sledges. Ropes, levers, and inclined planes were carefully used to maneuver stones into position, requiring both knowledge of physics and practical ingenuity. The Egyptians also employed measurement systems that allowed them to translate geometric concepts into practical construction techniques. Cubits, the standard unit of measure, were subdivided and applied consistently across projects. Ropes and plumb bobs ensured alignment, while leveling instruments allowed horizontal surfaces to be laid with remarkable accuracy. Even in the absence of modern mathematical notation, Egyptians demonstrated a deep understanding of ratios, proportions, and angles, integrating these principles into every stage of quarrying and construction. Quarrying itself was an art. Artisans would identify the natural fissures in stone and apply controlled pounding to separate blocks. In granite quarries, vertical channels were cut around desired blocks and then hammered with dolerite to loosen them. Workers understood how to prevent cracks that could render a block useless, and how to shape massive stones for transport and final placement. Transport across hundreds of kilometers of desert required both ingenuity and careful planning. Stones were floated down the Nile on specially constructed barges during seasonal floods, then dragged over sand using sledges, ropes, and manpower. Reliefs from tombs depict scenes of dozens or even hundreds of men coordinating their efforts, emphasizing the scale of labor management and teamwork required. The mastery of materials extended beyond simple carving and placement. Egyptians understood how stone could interact with other elements. For instance, limestone surfaces were polished with abrasive sand and water to achieve smooth finishes that reflected light, enhancing the visual impact of monuments. Granite obelisks were often polished and then inscribed with hieroglyphs using chisels and abrasives. The placement of these inscriptions required careful planning, as uneven pressure or misalignment could compromise readability or aesthetics. Each detail, no matter how small, reflected a civilization that valued precision, endurance, and visual harmony. Beyond quarrying and carving, Egyptians also innovated in joining and assembling stones. Dry-fit techniques allowed massive blocks to be stacked without mortar, relying on exact shaping and weight distribution to ensure stability. This required meticulous attention to tolerances. Variations of mere millimeters could compromise structural integrity. In some cases, copper clamps or dowels were used to secure blocks, demonstrating an understanding of mechanical fastening. Even the weight distribution within pyramids and temples reveals careful calculation, as internal chambers and corridors were engineered to prevent collapse, often employing corbelled ceilings and relieving chambers to manage structural stress. The training and knowledge transfer among Egyptian artisans were critical. Techniques were taught through apprenticeships, where young workers observed, practiced, and gradually mastered the craft under the guidance of experienced masters. Knowledge of stone properties, tool handling, and construction principles was encoded in practice rather than written manuals, yet it was remarkably consistent and reproducible across generations. This cumulative understanding enabled the construction of increasingly ambitious monuments over centuries. Experimental archaeology in modern times has confirmed many of these techniques. Researchers using replicas of copper chisels, dolerite pounders, and wooden sledges have successfully carved limestone and sandstone, moved large blocks over sand, and erected smaller-scale obelisks. These experiments reinforced the idea that Egyptian technology, while labor-intensive, was fully achievable with the tools and knowledge available. They also reveal the ingenuity required to adapt methods to different materials, environmental conditions, and project scales, a testament to a civilization that combined observation, experimentation, and disciplined application of knowledge. Finally, it is crucial to recognize that Egyptian mastery of materials and tools was inseparable from the cultural and religious context of their civilization. Every choice of stone, tool, and technique served a purpose beyond practicality. Granite was chosen for its durability to immortalize pharaohs. Limestone was polished and aligned to honor the gods. Sandstone temples were designed to reflect the permanence of divine order. Technology was a means to achieve spiritual and political objectives, demonstrating that for the Egyptians, engineering was both practical and symbolic. In conclusion, the advanced technology of ancient Egypt was not a product of chance or brute force. It was a sophisticated integration of material knowledge, tool mastery, observational insight, and cumulative experience. Each limestone block, sandstone pillar, and granite obelisk represents centuries of refinement, collaboration, and ingenuity. The Egyptians transformed natural resources into monumental architecture that combined durability, precision, and symbolic meaning, leaving a legacy that continues to inspire awe and study. To explore the materials and tools of ancient Egypt is to witness a civilization that understood its environment, harnessed its resources, and translated vision into enduring reality, a civilization where technology was not merely functional, but a reflection of culture, faith, and human ingenuity. The very act of moving a stone weighing several tons across hundreds of kilometers and then lifting it into precise alignment might seem impossible to modern observers. Yet for the ancient Egyptians, it was a challenge not of strength alone, but of ingenuity, planning, and mastery of natural forces. Their constructions, from the pyramids of Giza to the colossal obelisks of Heliopolis, demonstrate a level of coordination, technical knowledge, and practical problem-solving that remains extraordinary, even by today's standards. At the heart of Egyptian construction methods was an intimate understanding of physics, materials, and human labor. Stones quarried from distant sites had to be transported across desert terrain and along the Nile, often over distances exceeding hundreds of kilometers. Large limestone blocks might weigh several tons. Granite obelisks could weigh hundreds of tons. The challenge was not merely in lifting these stones, but in moving them efficiently, safely, and with the precision required to assemble monuments meant to endure for millennia. One of the most widely accepted methods involved the use of sledges. Stones were placed on wooden sledges, which were then pulled across sand by teams of workers. Reliefs from tombs depict dozens of men coordinating their efforts, sometimes with overseers ensuring timing and efficiency. Archaeological evidence suggests that wetting the sand in front of the sledges dramatically reduced friction, allowing a single worker to pull much more weight than dry sand would permit. This method illustrates a profound understanding of basic mechanics. By reducing resistance at the interface between stone and sand, the Egyptians multiplied the effectiveness of human effort without the need for complex machinery. Ramps were another critical component of construction. Various ramp designs have been proposed, including straight ramps, zigzagging ramps, and spiraling ramps surrounding pyramids. These ramps allowed blocks to be moved gradually upward, reducing the need for lifting at extreme heights. The construction and maintenance of ramps themselves required careful planning, as they had to support enormous weights and allow continuous movement of materials without collapsing. Archaeological studies and modern experiments have shown that with properly constructed ramps, teams could move multi-ton stones with relative efficiency, demonstrating that Egyptian ingenuity compensated for the absence of cranes. Levers and pulleys also played a central role. Lever systems allowed workers to lift, adjust, and position heavy stones with remarkable precision. By placing fulcrum strategically and applying force at optimal angles, artisans could achieve vertical placement or minor alignment adjustments. Pulleys, though simpler than modern block and tackle systems, were sometimes employed in conjunction with ropes to raise smaller blocks or guide stones into position. Together, levers, sledges, and ramps created a toolkit capable of transforming raw stone into perfectly aligned monumental architecture. The organization of labor was as important as the physical techniques employed. Egyptian construction projects relied on hierarchies of workers, skilled artisans, supervisors, engineers, and general laborers. Teams were divided according to tasks. Some quarried and shaped stones, others transported them, while another group focused on placement and alignment. This division of labor optimized efficiency, minimized errors, and allowed for large-scale projects to progress smoothly over years or even decades. Experimental archaeology has shown that such coordination is essential. Without clear management and task specialization, even relatively simple tasks become exponentially more difficult. Precision in alignment and placement was a constant concern. Pyramids, temples, and statues were not merely stacked haphazardly. Every block had to fit precisely, often with tolerances measured in millimeters. Ancient Egyptian builders employed leveling instruments, plumb bobs, and measuring rods to ensure accuracy. Surveying techniques were also used to maintain orientation over large areas. For example, the Great Pyramid's base is remarkably level, with differences of only a few centimeters across hundreds of meters, a feat that required careful observation, repeated measurements, and a sophisticated understanding of geometry. Transporting stones over long distances required careful consideration of both terrain and season. The Nile River was a vital artery, allowing massive stones from quarries in Aswan and Tura to be floated to construction sites during the annual flood season. Temporary canals, dredge channels, and specially designed barges facilitated movement, demonstrating that Egyptian construction methods integrated natural systems into logistical planning. Once on land, the challenge of moving stones over sand or uneven ground required not only manpower, but also an understanding of leverage, weight distribution, and traction. Erecting obelisks presented some of the most demanding engineering challenges. These monolithic pillars, carved from single blocks of granite, were transported and then lifted into a vertical position with astonishing precision. Scholars suggest that earthen ramps, levers, counterweights, and careful staging were combined to achieve this. Reliefs and depictions provide clues. Ropes were used to control movement, teams coordinated their effort in unison, and small adjustments were made iteratively to prevent catastrophic failure. Experimental reconstructions confirm that while labor-intensive, such feats are feasible using techniques within the Egyptians' technological repertoire. Another remarkable aspect of Egyptian construction methods was adaptability. Builders adjusted techniques based on the material, size, and destination of each block. Limestone blocks, easier to shape and lighter, were moved and placed differently than massive granite obelisks. Slopes, angles, and surfaces were carefully considered to optimize the effort required. This adaptability shows that Egyptian engineers were not rigidly bound by tradition, but employed observation, experimentation, and practical problem-solving to meet each unique challenge. Cultural and religious considerations also influenced construction techniques. Temples and pyramids were designed with symbolic and astronomical alignment in mind. Columns, walls, and statues were placed to correspond with cardinal points or celestial events, such as solstices or the rising of specific stars. Achieving these alignments required careful surveying, planning, and iterative adjustment. Technology was thus inseparable from cosmology, as the physical act of construction was also an expression of religious devotion and an effort to maintain cosmic order. Evidence of these methods comes not only from surviving monuments, but also from written records and archaeological finds. Quarry marks, inscriptions, and reliefs illustrate the steps involved in cutting, transporting, and erecting stones. Temporary ramps, sled tracks, and remnants of wooden scaffolding provide further proof of the techniques employed. Modern experimental archaeology has been able to replicate many of these processes, moving blocks of comparable weight over sand using sledges and water, erecting small-scale obelisks with levers, and aligning structures using primitive leveling instruments. These reconstructions confirm that Egyptian construction methods, while ingenious, were fully grounded in observation, skill, and practical knowledge. Yet perhaps the most striking aspect is the scale and coordination achieved. The Great Pyramid, with its millions of stones, required decades of sustained effort. Teams of workers had to be fed, housed, and organized efficiently. Supplies of stone, water, and tools had to be managed continuously. Over such periods, maintaining consistency in measurement, technique, and quality demanded a level of bureaucratic sophistication that rivals modern project management. Construction methods were thus a blend of technology, organization, and human ingenuity, all working in concert to produce enduring monuments. The Egyptians' mastery extended to finer details as well. Stones were polished, carved, and adjusted with patience and precision. Reliefs, inscriptions, and ornamental features were integrated seamlessly into larger structural frameworks. Even minor errors could compromise structural integrity or aesthetic quality, so iterative adjustment and careful planning were essential. The combination of macro-scale logistics and micro-scale craftsmanship is a hallmark of Egyptian construction, reflecting a civilization that understood both the immense and the minute. In conclusion, Egyptian construction methods reveal a civilization capable of moving the impossible. Through the careful use of sledges, ramps, levers, and manpower, the integration of natural forces and seasonal patterns, and the meticulous organization of labor and measurement, the Egyptians transformed raw stone into enduring monuments. These methods were not accidents or the result of brute force. They were deliberate, tested, and refined over centuries, combining observation, experimentation, and cumulative knowledge. The pyramids, temples, and statues of Egypt remain as enduring proof that human ingenuity, when guided by skill, planning, and vision, can achieve what might seem unimaginable. To witness Egyptian construction methods is to witness the convergence of engineering, culture, and faith, a civilization using the tools at its disposal to achieve perfection in scale, precision, and symbolism. In their methods, we see a remarkable integration of human capability, environmental understanding, and technological innovation, a model of applied knowledge that continues to inspire and mystify the modern world. The monuments of ancient Egypt are not only remarkable for their scale or material, but for the astonishing precision with which they were constructed. The alignment of pyramids, temples, obelisks, and statues often borders on perfection, their measurements precise to millimeters even across hundreds of meters. Achieving such accuracy without modern instruments is one of the greatest testimonies to the Egyptians' understanding of engineering principles, observation, and applied mathematics. Their precision was not accidental. It was a deliberate expression of both technical skill and cultural worldview. To appreciate the Egyptians' precision, one must begin with their units of measurement. The primary unit was the royal cubit, approximately 52.3 centimeters in length, divided into 7 palms and 28 fingers. Standardization of the cubit was essential. Cubit rods made of wood or stone, often embedded with markings, allowed architects and surveyors to maintain consistency across vast construction projects. These rods were carefully calibrated and monitored by overseers to ensure accuracy. The use of such standardized measures enabled massive monuments to be planned and executed with remarkable uniformity, despite involving thousands of workers over decades. Egyptians also developed tools to maintain alignment and leveling. Plumb bobs, essentially weighted pendulums, allowed vertical alignment to be assessed with high accuracy. A string with a suspended weight provided a straight line reference, enabling columns, walls, and statues to be erected perfectly vertical. Similarly, a leveling instrument, simple but effective, helped to create horizontal planes across large distances. Water-filled trenches or channels acted as primitive leveling devices, exploiting the principle that water seeks a level surface. Such techniques ensured that the base of a pyramid, for example, remained uniform to within a few centimeters, despite being constructed on uneven terrain. Geometry played a crucial role in achieving precision. Architects and engineers employed basic but powerful geometric principles, including right angles, triangles, and proportional divisions, to plan layouts, align stones, and calculate slopes. The Great Pyramid's slope angle, approximately 51 degrees, was carefully chosen to achieve structural stability while maintaining symmetry. Similarly, temple layouts often reflected proportional relationships that connected dimensions with symbolic or astronomical significance. While the Egyptians did not have formalized trigonometry as we understand it today, their practical knowledge of ratios, angles, and measurement allowed them to achieve results equivalent to precise geometric calculations. Astronomy was another essential component of engineering precision. Many Egyptian monuments were aligned with celestial bodies, often corresponding to solstices, equinoxes, or the rising of specific stars. Temples might be oriented so that sunlight illuminated key chambers at certain times of the year, while pyramids were aligned with cardinal points with remarkable accuracy. Observations of circumpolar stars, the sun, and the horizon informed both construction planning and ongoing measurements. This integration of astronomy and architecture reflects a worldview in which technology, religion, and cosmic order were inseparable. To construct with precision was to harmonize human activity with the universe itself. Consider the alignment of the Great Pyramid of Giza. Modern measurements indicate that its sides are oriented to true north with an error of less than 0.05 degrees. Achieving such accuracy without a compass or modern surveying equipment suggests that Egyptian engineers employed systematic astronomical observation. Techniques likely included tracking circumpolar stars to determine true north or using the sun's shadow to establish cardinal directions. Repeated measurements, adjustment, and verification ensured that the pyramid's orientation remained consistent across its massive footprint, an astonishing demonstration of applied observation and discipline. Precision extended beyond horizontal and vertical alignment. The placement of individual stones required careful consideration of weight distribution, interlocking angles, and surface smoothness. Blocks were often dressed to fit tightly with their neighbors, creating stable, mortarless assemblies. The accuracy of stone cutting allowed structures to endure millennia with minimal structural degradation. Misalignments or uneven placement could have caused catastrophic instability, so artisans continuously monitored, measured, and adjusted each stone as it was positioned. The Egyptians understood the importance of tolerances and iterative correction, applying what we might today recognize as quality control. Measurement precision also informed the construction of internal spaces. Passageways, chambers, and relief placements within pyramids and temples required accurate dimensions to serve both functional and symbolic purposes. Internal corridors were often engineered to exact lengths and slopes, sometimes integrating subtle astronomical alignments. The king's chamber in the Great Pyramid, for example, was constructed with remarkable internal alignment, ensuring structural integrity while reflecting symbolic geometry. Achieving such precision demanded meticulous planning, advanced knowledge of stone behavior, and continuous verification during construction. Engineering precision was also a product of cumulative knowledge. Techniques were refined over generations, passed from master to apprentice, and codified through practice rather than extensive written manuals. Observations of previous projects informed future improvements. Failures were studied and corrected, leading to gradual perfection in measurement, alignment, and material handling. This iterative process allowed the Egyptians to achieve feats that seem extraordinary even by modern engineering standards. Labor organization was critical to maintaining precision. Teams of artisans and laborers worked under supervisors who ensured consistency in measurements, placement, and finishing. Markings on stones, templates, and guides allowed different groups to coordinate their work seamlessly. Large-scale projects, such as the construction of pyramids or massive temples, required synchronization of thousands of workers over years or decades. Maintaining precision across such a scale demanded not only technical skill but also bureaucratic oversight, reflecting an advanced understanding of project management. The Egyptians also integrated precision into artistic elements. Reliefs, inscriptions, and ornamental features required exact placement to maintain aesthetic and symbolic coherence. Hieroglyphic inscriptions were spaced with consistent proportions, and decorative patterns aligned with architectural lines. Carving these elements into stone, already precisely cut and aligned, added another layer of complexity. This combination of engineering and artistry illustrates a holistic approach. Precision was not merely functional, but integral to cultural and religious expression. Experimental archaeology has validated many of these methods. Modern researchers have used replicas of plumb bobs, leveling instruments, and cubit rods to reproduce accurate alignments and placements. Even with these basic tools, observers can achieve alignments and dimensions comparable to those of the pyramids and temples. Such experiments confirm that Egyptian precision was achievable through careful observation, disciplined methodology, and cumulative expertise, rather than through luck or supernatural means. The precision of Egyptian engineering also extended to transportation and the positioning of stones. Calculating ramp slope angles, the number of laborers required to pull a block, and the force necessary to lift it into place all demanded precise knowledge of weight, friction, and leverage. Observing how sand, water, and ropes influenced movement allowed Egyptian engineers to refine techniques for both efficiency and safety. These calculations were conducted empirically through trial and error, observation, and adjustment, a process remarkably similar to modern engineering design principles. Finally, engineering precision in ancient Egypt was inseparable from cultural values and spiritual beliefs. Monuments were designed to endure for eternity, to reflect cosmic harmony, and to honor the gods. Measurement, alignment, and proportion were not merely technical concerns. They were moral and philosophical imperatives. By ensuring that temples, pyramids, and statues were precisely aligned and proportioned, the Egyptians reinforced a worldview in which order, stability, and perfection were central to both earthly governance and divine favor. Technology, religion, and ethics merged, resulting in constructions that were simultaneously practical, symbolic, and eternal. In conclusion, the engineering precision of ancient Egypt stands as one of the civilization's most remarkable achievements. Through standardized measurement systems, leveling techniques, geometric understanding, astronomical observation, and meticulous labor organization, the Egyptians created monuments that remain unparalleled in scale, alignment, and durability. Their precision was not incidental. It was the result of centuries of accumulated knowledge, disciplined application, and cultural vision. To study these methods is to witness a civilization that mastered both the material and the intangible, blending mathematics, observation, and faith into constructions that continue to inspire awe and wonder in the modern world. Precision, in ancient Egypt, was more than technical skill. It was a reflection of a civilization's ability to translate vision into reality with unmatched rigor, foresight, and reverence. Each perfectly aligned stone, each carefully measured corridor, and each monument that has endured millennia stands as evidence of a society that valued knowledge, discipline, and harmony with the cosmos. In this, Egyptian engineering precision is not only a technical achievement, but a cultural and philosophical statement, one that continues to captivate, challenge, and inspire those who seek to understand the heights of human ingenuity. To understand the genius of ancient Egyptian technology, it is illuminating to place it in the context of other contemporary civilizations. The Nile Valley was not the only cradle of human innovation. Mesopotamia, the Indus Valley, and ancient China all produced remarkable feats of architecture, engineering, and organization. Yet Egypt's monuments stand apart. not only in scale and durability, but in the synthesis of materials, labor, measurement, and cosmology that they embody. Comparative analysis reveals how Egypt's civilization combined technical mastery with cultural, religious, and philosophical purpose to create something truly unparalleled. Consider Mesopotamia, often regarded as the cradle of civilization. The Sumerians, Akkadians, and Babylonians engineered impressive structures, most notably the ziggurat, S-tiered temple platform rising above city centers. Ziggurats served religious and civic functions, and their construction required an understanding of brickmaking, leveling, and drainage. Yet, compared to Egypt, Mesopotamian monuments rarely achieved the same scale or enduring precision. The mud brick used in ziggurats, though practical for the region, eroded over time, leaving few structures standing in their original form. Egypt, by contrast, utilized stone, limestone, sandstone, and granite, which, combined with precise placement and interlocking techniques, enabled monuments to survive for millennia. While Mesopotamia excelled in urban planning and hydraulic engineering, Egypt's technological achievements were distinguished by permanence and monumental scale. Similarly, the Indus Valley Civilization, flourishing around 2500 to 1900 BCE, displayed remarkable urban sophistication. Cities such as Mohenjo-daro and Harappa featured planned street grids, standardized bricks, and advanced drainage systems. These innovations demonstrate a high degree of social organization and technical understanding. Yet Egyptian constructions differed fundamentally in purpose and scope. While the Indus Valley focused on functional infrastructure to support urban life, Egypt's monumental architecture served dual purposes: practical, providing tombs, temples, and ceremonial spaces, and symbolic, projecting divine authority, cosmic harmony, and societal values. The Egyptians' integration of engineering with cosmology, religious ritual, and social hierarchy sets them apart in both ambition and conceptual depth. In ancient China, early dynasties such as the Shang and Zhou achieved impressive feats of bronze casting, walled cities, and ceremonial complexes. Chinese engineers demonstrated skill in metallurgy, irrigation, and fortification. Yet Egyptian monumental engineering, particularly in moving massive stones, constructing pyramids, and erecting obelisks with precise alignment, achieved a degree of scale and precision unmatched by contemporaneous civilizations. The Egyptians' ability to integrate construction methods, precision measurement, and astronomical alignment created structures that were both physically and symbolically enduring. Egypt's unique combination of labor, materials, measurement, and cultural integration is particularly evident in pyramid construction. While other civilizations built large structures, the Great Pyramid of Giza remains a singular achievement. Containing approximately 2.3 million stones, each weighing several tons, its base covers more than 5 hectares, and its sides are aligned with cardinal points with astonishing precision. This level of planning and execution required not only skilled artisans and tools, but also a deep understanding of geometry, surveying, and human organization knowledge accumulated and refined over generations. Few other civilizations produced comparable structures that survived so intact and precise for over 4 millennia. Colossal statues and obelisks further illustrate Egypt's uniqueness. Ramses II statues, some over 20 meters tall, and obelisks carved from single granite blocks, required not only advanced quarrying techniques, but also precise transportation and erection methods. While Mesopotamia, the Indus Valley, and other regions produced impressive sculpture, few achieved the combination of monumental scale, fine detail, and durability seen in Egypt. Granite, notoriously difficult to work, was transformed into enduring symbols of pharaonic power, demonstrating both technical mastery and symbolic intent. Another distinguishing factor is the integration of astronomy and cosmology into construction. While other civilizations observed celestial phenomena, the Egyptians systematically incorporated these observations into their architecture. Temples, pyramids, and obelisks were aligned to stars, solstices, and cardinal points, reflecting a worldview in which the heavens and the earth were interconnected. This integration of engineering with spiritual and cosmological principles is rare in ancient civilizations. In Egypt, technology was inseparable from philosophy, religion, and governance, creating monuments that were simultaneously functional, symbolic, and eternal. The labor organization also highlights Egypt's distinctiveness. The scale of construction required tens of thousands of workers, coordinated over decades. Teams were specialized, supervised, and meticulously planned. Seasonal flooding of the Nile provided a reliable labor pool, freeing agricultural workers for construction during non-farming periods. Other civilizations relied on labor in different ways, often through conscription or smaller-scale projects. Egypt's system, integrating seasonal labor cycles, skilled artisanship, and bureaucratic oversight, allowed sustained, large-scale projects with unprecedented precision and endurance. Furthermore, Egypt's cumulative approach to technology distinguishes it from contemporaries. Knowledge of quarrying, carving, transportation, measurement, and alignment was transmitted across generations, refined through experimentation and observation. Each construction project built upon the successes and lessons of the previous, enabling increasingly ambitious achievements. This continuity, combined with a centralized authority under pharaohs, ensured that technological knowledge was preserved, codified in practice, and applied at ever larger scales. Other civilizations, while innovative, often lacked the same continuity or integration of knowledge, resulting in brilliant but comparatively isolated achievements. Egyptian engineering was also remarkable in its balance of practicality and aesthetics. Every monument, from massive pyramids to intricately carved temple reliefs, reflected both technical precision and artistic intention. Proportions, symmetry, and alignment were carefully controlled, not only to ensure structural stability, but also to convey religious and social meaning. In comparison, other civilizations often emphasized either functional infrastructure or ceremonial grandeur, rarely achieving the seamless integration of utility, durability, and symbolic resonance characteristic of Egyptian construction. The Egyptians' ability to work with massive stone blocks over long distances is another distinguishing factor. While Mesopotamia and the Indus Valley relied primarily on brick or smaller stone, Egypt transported granite blocks hundreds of kilometers from Aswan to Giza using barges, sledges, and ramps. Obelisks, sometimes weighing hundreds of tons, were carved, transported, and erected with precision that continues to challenge modern engineers. This combination of quarrying, transportation, and placement represents an integration of knowledge, labor, and ingenuity that few civilizations matched. Even in urban planning, Egypt demonstrated unique approaches. While not as dense as Indus Valley cities, temple complexes and necropolises were designed with precise orientation, proportionality, and alignment to natural features. The placement of tombs, temples, and monuments followed both practical and symbolic logic, reinforcing societal hierarchies and cosmic order. This systematic integration of environment, architecture, and ritual was exceptional and contrasts with the more functionalist or defensive focus of contemporary civilizations. In terms of technological philosophy, Egypt stands apart for its focus on permanence. While other civilizations innovated for immediate utility or ceremonial purposes, Egypt invested in structures meant to last for eternity. Pyramids, temples, and statues were conceived with millennia in mind. This long-term perspective shaped every aspect of construction, from material selection to precision in alignment, from workforce organization to cumulative knowledge transfer. The Egyptians' technological choices were deeply intertwined with spiritual and cultural imperatives, making their engineering achievements a reflection of civilization itself. Comparative analysis also highlights Egypt's ability to adapt and innovate. Techniques evolved to meet the challenges posed by different materials, scales, and environmental conditions. Quarrying methods, transport systems, and construction techniques were modified to suit granite versus limestone, obelisks versus pyramids, river transport versus desert hauling. This adaptability, combined with systematic observation and trial and error refinement, allowed Egypt to achieve technical feats that remain astonishing today. Finally, the enduring legacy of Egyptian technology underscores its uniqueness. While Mesopotamian ziggurats collapsed, Indus Valley cities were abandoned and partially eroded, and early Chinese fortifications were often temporary. Egyptian monuments endure. Pyramids, obelisks, and temples have survived thousands of years, preserving knowledge of engineering, mathematics, and culture. This endurance is not merely physical. It also represents the persistence of an integrated technological and cultural vision unparalleled in the ancient world. In conclusion, when placed in comparative perspective, Egypt's technological achievements stand apart not solely for their scale, but for the synthesis of materials mastery, labor organization, measurement precision, astronomical integration, cultural purpose, and long-term vision. While other civilizations produced remarkable innovations, Egypt uniquely combined engineering, art, religion, and administration into enduring monuments. Their technology was not an isolated skill, but a reflection of a civilization capable of harmonizing observation, experimentation, organization, and ideology into tangible, lasting expressions of human ingenuity. Egypt's monuments continue to awe and inspire because they embody this integration. They are not merely structures. They are statements about a civilization that understood its environment, harnessed its resources, coordinated its people, and pursued precision, beauty, and permanence with unmatched discipline. The comparative analysis reveals that ancient Egypt's advanced technology was not only effective and innovative, but profoundly distinctive. A civilization in which every stone, every measurement, and every alignment bore witness to a holistic mastery of human knowledge and ambition. Despite centuries of study, excavation, and experimentation, many aspects of ancient Egyptian technology remain shrouded in mystery. The surviving monuments, pyramids, obelisks, colossal statues, and temples offer extraordinary evidence of skill and ingenuity, yet they also raise as many questions as they answer. How did the Egyptians quarry, transport, and place stones weighing tens or even hundreds of tons? How did they achieve near-perfect alignment with the cardinal points and celestial events without modern instruments? What practical knowledge, buried with generations of artisans, allowed them to perform feats that still challenge contemporary engineers? The mystery begins with scale. The Great Pyramid of Giza alone comprises approximately 2.3 million limestone blocks, with each averaging 2.5 tons. Granite blocks in internal chambers and obelisks often weigh more than 50 tons, with some approaching 200 tons. Moving, lifting, and positioning these stones with the precision we observe today requires not only raw labor, but a sophisticated understanding of leverage, mechanics, and material properties. Archaeologists and engineers have proposed ramps, sledges, levers, and water lubrication techniques, and experimental reconstructions demonstrate their feasibility. Yet no single explanation fully accounts for the consistency, efficiency, and accuracy achieved across centuries of monumental construction. Some techniques may have been deliberately esoteric, restricted to select groups of master artisans. Knowledge in ancient Egypt was often transmitted orally through apprenticeships, encoded in practice rather than in written manuals. Temples and royal workshops likely functioned as centers of technical learning, where methods were preserved, refined, and guarded. As generations passed, some of this specialized knowledge may have been lost due to political upheavals, invasions, or the natural fading of oral traditions. What we see today, massive structures and precise alignment, is therefore the visible residue of knowledge whose origins and full scope remain partially obscured. Quarrying techniques, particularly for granite and Aswan, continue to puzzle researchers. Granite is exceptionally hard, yet Egyptians managed to extract enormous monolithic blocks with copper chisels, dolerite pounders, and abrasive sand. Evidence suggests they exploited natural fissures and applied controlled fracturing to separate stones. Still, questions remain about how precision was maintained at such scales. The removal of a single misaligned or cracked block could jeopardize the entire project, yet the consistency across monuments indicates not chance, but a systematic mastery of stone behavior. Some scholars speculate that additional, now-lost tools or techniques, perhaps specialized wedges, chemical treatments, or methods for softening stone, may have existed but left no trace. The transportation of massive stones presents another enigma. Obelisks carved from single blocks in Aswan were floated down the Nile during the inundation season, then hauled across desert terrain to their final locations. Reliefs depict teams of men dragging sledges with ropes, and experimental archaeology confirms that wetting the sand reduces friction. Yet the precise coordination required to move multi-ton blocks over long distances without modern vehicles, while maintaining orientation and avoiding damage, is staggering. Detailed instructions may have been preserved in workshops or guilds and lost over time, leaving modern scholars to reconstruct methods through inference and experimentation. Erecting obelisks further exemplifies lost knowledge. These monolithic pillars were raised upright with astonishing accuracy, their bases perfectly level, and their tips aligned with minimal deviation. Theories suggest a combination of ramps, levers, counterweights, and scaffolding, but the exact procedures, especially for the largest obelisk, remain unknown. Ancient depictions hint at teamwork, rope systems, and precise staging, yet they offer only partial insight. The fact that such feats were repeated consistently over centuries implies a set of instructions or experiential knowledge no longer extant. Even pyramid construction continues to harbor unresolved mysteries. The Great Pyramid's internal chambers, passageways, and relieving structures reveal a level of planning that transcends simple block stacking. Engineers debate how blocks were lifted to higher levels and how the internal layout was executed without misalignment. The precision of the king's chamber, the corbelled ceilings, and the alignment with cardinal points suggest that Egyptian architects possessed a sophisticated combination of mathematics, surveying techniques, and observational methods that have been partially lost to history. Mathematics itself presents a mystery. While hieroglyphic numerals and basic arithmetic operations are documented, the full extent of Egyptian geometric knowledge, especially as applied to large-scale construction, is inferred from monuments rather than fully recorded texts. Ratios, slope calculations, and alignment techniques were clearly understood and consistently applied, yet the precise methods of calculation, verification, and correction remain speculative. Modern reconstructions provide plausible methods, but the seamless integration of theory and practice seen in the monuments indicates a level of procedural knowledge that is no longer directly accessible. Astronomical alignment adds another layer of mystery. Temples and pyramids are often oriented toward specific stars or celestial events, such as the solstices or the rising of Sirius. Achieving these alignments required careful observation, repeatable measurement, and systematic adjustment over long periods. How such an observation was translated into construction procedures remains unclear. Did Egyptian engineers rely on sighting rods, water levels, shadow tracking, or other devices? Reliefs depict observers and instruments, but the exact processes for converting celestial positions into precise physical orientations are partially speculative, hinting at knowledge that has been lost with time. Tool marks and inscriptions provide tantalizing clues. Quarry walls reveal repeated pounding, chisel use, and abrasion patterns, suggesting methodical processes. Temple reliefs and tomb illustrations depict artisans, sledges, and ropes, hinting at coordinated techniques. Yet these clues are fragmentary, leaving gaps in understanding. Some researchers suggest that certain tools or methods were ceremonial as well as practical, intertwined with ritual practice, and therefore not fully documented for posterity. Knowledge may have been intentionally esoteric, restricted to select groups to preserve spiritual and political power. The mystery extends to project management. Large-scale construction projects required meticulous scheduling, workforce allocation, resource logistics, and oversight. Egyptian administrators coordinated laborers, supplied food and water, maintained tools, and ensured continuity over decades-long projects. While administrative records, such as work rosters, exist, the full scope of planning, contingency management, and knowledge transfer is incompletely understood. How did they maintain consistency in quality, precision, and alignment across multiple projects separated by geography and time? The answer lies in organizational knowledge, much of which has been lost. Even seemingly simple tasks carry enigmas. How did teams ensure that the base of a pyramid remained level across hundreds of meters? How did they fit massive blocks together with millimeter precision without modern measuring instruments? How were errors corrected during construction without disrupting ongoing work? These questions highlight that much of the practical, experiential knowledge of Egyptian artisans' trial and error refinements, iterative measurement, adjustments, and verification has disappeared, leaving only the tangible results, monuments that embody knowledge now partly lost to time. The loss of knowledge is compounded by the passage of centuries, invasions, and cultural shifts. Many workshops, texts, and oral traditions disappeared as dynasties fell, tombs were looted, and sacred knowledge was guarded or destroyed. Modern understanding is pieced together from surviving artifacts, texts, and experimental archaeology, but gaps remain. Every modern theory about construction methods is an approximation, informed by observation, experimentation, and inference. The Egyptians themselves may have considered some techniques sacred, intentionally leaving them undocumented to preserve mystical or political authority. Yet, despite these mysteries, enough evidence exists to recognize a civilization of extraordinary skill and insight. The precision, scale, and durability of Egyptian monuments testify to a knowledge system that integrated materials science, mechanics, mathematics, and astronomy in ways that remain extraordinary today. The lost knowledge is not necessarily magical. It is a combination of observation, empirical learning, iterative refinement, and disciplined practice, much of which simply was not recorded in a manner that survived the millennia. Experimental archaeology continues to illuminate aspects of this lost knowledge. Projects using copper chisels, wooden sledges, dolerite pounders, ramps, and water lubrication have successfully recreated limestone and sandstone construction techniques. Miniature obelisks have been raised using levers and rope systems. These experiments confirm that Egyptian technology was grounded in practical observation and engineering logic, rather than supernatural intervention. Yet, even with these reconstructions, the scale, coordination, and cumulative wisdom required for the largest monuments remain challenging, hinting at knowledge partially obscured by time. Cultural and spiritual factors may have contributed to the secrecy or loss of knowledge. Construction was inseparable from religious and political authority. Monuments were built to honor gods, immortalize pharaohs, and maintain cosmic order. Knowledge of construction techniques may have been intertwined with ritual practice, making it esoteric, symbolic, or restricted to certain priestly or artisan groups. This intentional limitation of knowledge, combined with natural decay over centuries, has left modern observers piecing together methods from remnants, inscriptions, and surviving structures. Finally, the mystery of lost knowledge serves as a reminder of human ingenuity and the limits of historical understanding. Egyptian monuments endure as silent testimony to techniques that are partly known, partly inferred, and partly forever lost. Each stone, alignment, and carving carries the legacy of centuries of observation, experimentation, and refinement. Yet much of the reasoning and procedural wisdom behind these feats is irretrievable. The challenge for modern scholars, engineers, and enthusiasts is to reconstruct, understand, and appreciate this lost knowledge not merely as an academic exercise, but as a window into the minds of one of history's most remarkable civilizations. The technology of ancient Egypt is as much about what we do not know as what we can observe. Quarrying, transport, alignment, and construction methods were achieved with skill and precision that continues to inspire wonder, yet the full scope of practical knowledge remains partially hidden by time. Lost techniques, esoteric practices, and undocumented methods form a silent thread connecting every surviving monument. By studying the tangible evidence, conducting experimental reconstructions, and reflecting on the scale and precision of Egyptian achievements, we gain glimpses into a world where knowledge was as monumental as the structures it produced, a civilization whose ingenuity, patience, and understanding of natural forces continue to mystify and inspire millennia after its prime. In ancient Egypt, technology was never an end in itself. Every architectural choice, measurement, and construction technique was inseparable from a civilization's spiritual beliefs and societal organization. Monuments, temples, pyramids, and statues were simultaneously practical constructions, artistic expressions, and tangible manifestations of devotion to gods and kings. To understand Egyptian engineering, it is essential to understand this integration. The alignment of stones, the precision of measurements, and the scale of projects were all reflections of cultural values, religious ideology, and social hierarchy. At the heart of Egyptian civilization was the pharaoh, a ruler considered divine, whose authority extended into both the mortal world and the afterlife. The pharaoh was not merely a political figure, but a central figure in a cosmic order. Technology and labor were mobilized to honor this authority, often in the construction of monuments intended to last for eternity. Pyramids, for instance, were not simply tombs. They were physical embodiments of the pharaoh's divinity, designed to ensure a safe passage to the afterlife, to connect the mortal realm with the divine, and to symbolize the eternal order of Ma'e, the principle of truth, balance, and cosmic harmony. Temples, too, were deeply intertwined with religious practice and symbolism. The orientation, dimensions, and construction materials of each temple were chosen not solely for durability or aesthetics, but to reflect spiritual meaning. Temples often aligned with celestial phenomena, the rising sun on the solstice, or the appearance of a specific star, linking the earthly realm with the heavens. This alignment was not accidental. It required meticulous observation, planning, and engineering precision. Technology, in this context, was a conduit for devotion. To build accurately was to honor the gods, to harmonize with the cosmos, and to reinforce the social and spiritual order. Obelisks, monolithic pillars carved from single blocks of granite, exemplified this integration of technology and religious significance. Rising tens of meters, these monuments were inscribed with hieroglyphs praising pharaohs and deities. Their placement at temple entrances, often aligned with solar paths, created visual and symbolic connections between the human and divine. The technical challenge of quarrying, transporting, and erecting these monoliths served a higher purpose: the physical demonstration of piety, the projection of power, and the embodiment of cosmic principles. Technology and faith were inseparable, each reinforcing the other. The act of construction itself was a ritualized process. Workers, artisans, and supervisors participated in highly structured labor systems, often synchronized with the agricultural calendar and the seasonal inundation of the Nile. This system ensured not only efficiency, but also order and discipline, mirroring the social hierarchies established by religious and political authority. The labor required to move and position multi-ton stones, carve intricate reliefs, and maintain alignment demanded cooperation, precision, and shared purpose. In essence, engineering became a form of collective devotion, a tangible expression of loyalty to both king and deity. The design of Egyptian monuments further illustrates the inseparability of technology and symbolism. Pyramids, for example, were not merely geometric marvels, they were cosmic diagrams. The shape itself represented the descending rays of the sun, connecting the pharaoh with Ra, the sun god. Internal chambers and passageways were designed with both functional and symbolic intent, guiding the pharaoh's soul towards celestial eternity. Temple layouts often mirrored the universe in miniature. Sanctuaries represented the primeval mound of creation. Columns reflected the primordial papyrus and lotus, and reliefs depicted divine narratives in proportionally harmonious arrangements. Every engineering decision reinforced religious meaning. Hieroglyphic inscriptions and reliefs provide further evidence of technology as devotion. These texts often commemorate the pharaoh's accomplishments, the favor of the gods, or the cosmic significance of specific structures. Carving hieroglyphs into stone required not only artistic skill, but technical understanding. Precise spacing, orientation, and alignment ensured legibility and aesthetic harmony. Even minor miscalculations could compromise the visual and symbolic impact. In this sense, technology served both practical and devotional functions, allowing artisans to immortalize divine and royal authority in enduring form. The use of astronomical alignment was deeply symbolic. Temples often oriented towards solstices or star risings associated with gods, linking human activity with celestial cycles. The Great Temple of Karnak, for instance, aligns with the winter solstice sunrise, allowing sunlight to illuminate the sanctuary in a dramatic, almost mystical display. Achieving such alignment required detailed observation, precise measurement, and careful construction techniques. Technology was not an afterthought, but a vehicle for expressing spiritual truths. Precision in measurement mirrored cosmic order, and architectural mastery reflected divine harmony. Even everyday technology, irrigation systems, stone carving techniques, and measurement tools were infused with cultural and religious significance. The Nile's flooding, carefully managed through canals and basins, was perceived as a manifestation of divine favor. Harnessing water and shaping land were acts of control over the natural world, reflecting both technical skill and spiritual order. Similarly, tools such as plumb bobs, leveling instruments, and cubit rods were not merely practical. Their use embodied a disciplined, almost ritualized approach to creation, ensuring that human constructions reflected divine perfection. The social hierarchy underpinning Egyptian technology reinforced its religious function. Artisans and laborers were organized under skilled overseers, whose authority derived from both technical expertise and spiritual sanction. Labor was not anonymous. Each worker participated in a larger narrative of devotion and cosmic order. Seasonal labor mobilization, combined with hierarchical oversight, created a system in which technology served as a medium for expressing social and religious values. The monuments themselves became physical evidence of a civilization's collective faith, discipline, and organization. Cultural significance also extended to material choice. Granite, limestone, and sandstone were selected not only for durability, but for symbolic meaning. Granite, quarried in Aswan, was associated with permanence and divine strength, limestone with light and sacredness, sandstone with earthly endurance. The very materials of construction communicated spiritual messages, reinforcing the interplay between technology, culture, and religion. By manipulating these materials with precision, Egyptians created monuments that embodied both technical skill and symbolic power. Rituals often accompanied construction. Offerings, prayers, and ceremonies were performed to ensure divine approval and success. This ritualized approach suggests that technology was experienced as a sacred act, a collaboration between human skill and divine favor. The meticulous measurement, precise alignment, and careful execution of construction tasks were expressions of reverence as much as engineering excellence. In this way, technology was a spiritual discipline, reinforcing cultural and religious values through material practice. Artistic integration also reflects the inseparability of technology and devotion. Reliefs, statues, and inscriptions were meticulously designed to maintain proportion, symmetry, and harmony within architectural spaces. These artistic decisions required technical understanding of angles, measurement, and spatial relationships. Accuracy was not purely functional, it was devotional, ensuring that the aesthetic and symbolic impact of the monument aligned with spiritual intent. Precision in stone cutting, carving, and placement became a form of sacred craftsmanship, linking the physical and metaphysical realms. Even funerary practices underscore the integration of technology and religion. Tombs were constructed with precise dimensions, orientation, and internal layout to facilitate the pharaoh's journey to the afterlife. Burial chambers, corridors, and shafts reflected cosmological symbolism and engineering knowledge simultaneously. Constructing these tombs required mastery of stonework, measurement, and logistics, yet the ultimate purpose was spiritual, ensuring the eternal survival of the soul and maintaining cosmic order. Technology, in this context, was inseparable from belief, and technical skill became an instrument of devotion. The long-term durability of monuments further reinforces their cultural significance. By constructing temples and pyramids to last millennia, the Egyptians created enduring symbols of faith, power, and cosmic harmony. Precision, scale, and material choice were not mere technical considerations, they were acts of devotion. Each enduring stone communicated continuity, order, and eternal reverence, reflecting a civilization in which technology served higher spiritual purposes. The integration of technology with social, political, and religious systems also fostered cohesion. Monuments and temples served as centers for rituals, education, and administration. Their construction reinforced hierarchical structures, mobilized communities, and reflected collective values. By embedding technological mastery within cultural and spiritual frameworks, Egypt ensured that its achievements were not only practical and monumental, but also socially and religiously meaningful. In conclusion, the cultural and religious significance of Egyptian technology cannot be overstated. Engineering, measurement, material selection, and construction methods were all deeply intertwined with faith, symbolism, and social order. Monuments were simultaneously practical, artistic, and devotional, reflecting a civilization in which technology served as a medium for expressing cosmic, political, and spiritual ideals. To study Egyptian engineering is to witness not only technical skill, but a worldview in which human ingenuity, religious devotion, and societal organization converge to create structures of enduring beauty, meaning, and awe. In Egypt, every perfectly aligned stone, every massive obelisk, and every intricately carved temple is a testament to a culture that saw technology not as a neutral tool, but as a sacred instrument. To build with precision was to honor the gods. To construct with care was to maintain Ma'at, the cosmic order. To mobilize labor was to affirm social hierarchy. The monuments endure because they were built for eternity, integrating technical mastery with spiritual purpose, a civilization where technology, faith, and culture were inseparable. In the modern era, the marvels of ancient Egyptian technology continue to inspire awe, curiosity, and rigorous investigation. Engineers, archaeologists, and enthusiasts seek to understand how a civilization without modern machinery, electricity, or advanced metallurgy managed to achieve feats that continue to challenge contemporary understanding. The field of experimental archaeology has emerged as a vital avenue for uncovering the practical knowledge embedded in Egypt's monumental constructions. By reconstructing methods, materials, and processes, scholars attempt to bridge the temporal gap, transforming speculation into demonstrable understanding. The goal of modern reconstructions is not merely academic. It is an attempt to experience, in some measure, the physical and intellectual challenges faced by Egyptian artisans. By moving blocks, carving stone, or erecting obelisks using only tools and techniques available to the ancient world, researchers can assess the plausibility of historical hypotheses. These experiments reveal the ingenuity, patience, and organizational sophistication necessary to execute large-scale projects. They also illuminate the subtle integration of materials science, geometry, and labor coordination that characterized Egyptian technology. One of the most significant areas of reconstruction involves stone quarrying. Granite, quarried in Aswan, is exceptionally hard, yet Egyptians transformed it into obelisks, sarcophagi, and statues with remarkable precision. Modern experiments replicate quarrying with dolerite pounders, copper chisels, and sand abrasives. Researchers have successfully separated granite blocks, demonstrating that careful percussion, combined with knowledge of natural fissures, can yield usable stones without advanced metallurgy. These experiments confirm that Egyptians relied on observation, practical trial and error, and empirical understanding of stone properties rather than magic or advanced lost technologies. Transporting massive stones represents another critical focus of modern reconstruction. Obelisks, sometimes weighing over 200 tons, were carved hundreds of kilometers from quarries in Aswan to locations such as Karnak or Luxor. Archaeologists and engineers have tested the feasibility of sledges, rollers, ropes, and lubrication with water to reduce friction on sand. Experiments demonstrate that teams of workers can move multi-ton blocks using these methods, validating historical accounts and depictions found in reliefs. Yet, even with these reconstructions, the scale and coordination required remain extraordinary, offering insight into the meticulous planning and organizational skill inherent in Egyptian construction. Moving stones along the Nile also involved sophisticated logistical planning. Barges constructed from wood, secured with ropes, and carefully balanced, carried monolithic blocks downstream during the inundation season. Modern experiments with replicas of such vessels reveal that ancient engineers understood buoyancy, load distribution, and river dynamics. By combining practical observation with seasonal cycles, they ensured that transport was efficient and relatively safe. These reconstructions highlight the Egyptians' integration of natural forces into technological solutions, exploiting the environment to achieve monumental tasks. Erecting obelisks remains one of the most compelling demonstrations of Egyptian ingenuity. Contemporary projects have raised miniature obelisks using ramps, levers, and counterweights, showing that these methods were feasible with disciplined labor and careful measurement. While modern engineers can provide mechanical advantages, experiments adhering strictly to ancient methods demonstrate that alignment, verticality, and stability could be achieved through coordinated effort and understanding of physics. These reconstructions lend credence to historical claims, showing that the Egyptians' feats were rooted in empirical knowledge, creativity, and collective skill. Pyramids, the most iconic of Egyptian monuments, have also been the subject of extensive reconstruction studies. Scholars have explored multiple hypotheses: straight ramps, zigzagging ramps, internal spiral ramps, and counterweight systems. Miniature models and partial reconstructions demonstrate that each method is theoretically viable, but the practical execution would require precise measurement, rigorous planning, and highly coordinated labor. Experiments reveal how teams could maintain alignment, slope, and level surfaces, validating the Egyptians' understanding of geometry, structural principles, and workforce management. Carving limestone with copper chisels and abrasives offers another fascinating glimpse into ancient methods. Modern artisans replicate the process, confirming that even without iron or steel, precise carving and intricate reliefs are achievable. The experiments highlight the role of patience, repeated application, and strategic use of tools and abrasives. Reliefs, inscriptions, and sculptural details on temples and tombs were thus the product not of magical skill, but of disciplined, methodical practice. Observing the effort required reinforces an appreciation for the technical competence of ancient artisans. Modern reconstructions also explore the integration of astronomy into construction. Researchers simulate alignments with stars, solstices, and cardinal points, using sighting instruments comparable to rods, plumb lines, and water levels documented in archaeological records. These experiments demonstrate that Egyptian architects could align massive structures with celestial precision, combining observational astronomy with measurement techniques and geometric calculation. By replicating the process, scholars gain insight into the interplay between practical engineering and cosmological purpose in Egyptian technology. Beyond tools and materials, modern reconstructions illuminate social and organizational dimensions. Managing thousands of workers over decades required hierarchical oversight, clear division of labor, and systematic scheduling. Experiments involving large teams moving blocks or assembling structures reveal the necessity of coordination, communication, and standardization. Ancient administrators likely employed similar strategies, organizing labor by specialization, synchronizing activities, and ensuring continuity across generations. Technology, in Egypt, was inseparable from social infrastructure and management capability. Experimental archaeology also addresses questions of sustainability and material efficiency. Reconstructions of quarrying, transport, and construction reveal that Egyptians optimized resource use, balancing effort, materials, and labor. Water, sledges, ramps, and manpower were leveraged to minimize waste and maximize efficiency. The placement of quarries near rivers, the timing of labor with seasonal floods, and the selection of stone types all demonstrate a sophisticated understanding of resource management. Modern experiments underscore that Egyptian technology was not only effective, but also highly efficient within environmental and social constraints. Modern scholars have also recreated entire architectural elements. Columns, lintels, and temple facades have been constructed using only ancient methods, showing that precise alignment, load distribution, and aesthetic proportion could be achieved without modern engineering tools. These reconstructions confirm that the grandeur of Egyptian monuments arose from cumulative knowledge, empirical observation, and disciplined practice rather than chance. They also provide practical insight into the challenges faced by workers, deepening appreciation for the complexity of Egyptian engineering. Each successful reconstruction reinforces a central lesson. Egyptian technology was neither magical nor accidental. It was grounded in systematic observation, empirical experimentation, and coordinated labor. Tools were simple, but applied with insight. Materials were basic, but exploited with understanding. And human organization amplified capability beyond what individual effort could achieve. Modern experiments translate this wisdom into observable processes, bridging millennia to reveal the mechanics, strategies, and practical knowledge behind monumental constructions. Yet, even with modern reconstructions, mysteries remain. Large-scale projects, such as the transportation of the largest obelisks or the construction of the Great Pyramid's internal chambers, challenge contemporary engineers using purely ancient methods. The precise coordination, timing, and cumulative knowledge that allowed these projects to succeed in antiquity are difficult to replicate fully today. Each experiment provides partial insight, emphasizing that Egyptian technology was not only about tools, but about human ingenuity, discipline, and knowledge preserved across generations. Modern reconstructions also inspire contemporary engineering, material science, and project management. Lessons from sledges, ramps, lever systems, and modular labor allocation inform modern understanding of logistics and mechanical advantage. The Egyptians' approach to problem-solving, empirical observation, iterative refinement, and integration of natural forces offers insights that transcend time, illustrating universal principles of engineering and organization. In this sense, reconstructing ancient technology is not only a historical exercise, but also a study in timeless ingenuity. Experimental projects also highlight the human element. Workers, foremen, and master artisans were deeply engaged in both physical and intellectual labor. Coordinating teams of hundreds or thousands required trust, skill, and communication. Modern reconstructions, by simulating these social dynamics, demonstrate that technology in ancient Egypt was as much about people and organization as it was about stones and tools. The monuments endure not merely because of material strength, but because of cumulative human knowledge, discipline, and cooperation. Finally, modern reconstructions serve an educational and inspirational purpose. By replicating ancient techniques, scholars, students, and enthusiasts gain a tangible understanding of Egyptian ingenuity. Observing a miniature obelisk being raised, a granite block being quarried, or a temple facade being constructed with copper tools fosters a visceral connection to the civilization. It transforms abstract admiration into experiential appreciation, revealing that the brilliance of Egypt lies not in mystique, but in the application of knowledge, observation, and human effort. The Egyptians' ability to integrate observation, experimentation, and organization resulted in monuments that endure millennia, inspiring awe and inquiry. These reconstructions affirm that Egyptian technology was not accidental or supernatural, but a testament to human ingenuity, persistence, and the seamless integration of culture, faith, and practical knowledge. Through experimental archaeology, we glimpse a civilization whose understanding of materials, mechanics, and organization remains instructive and inspiring today. Every reconstructed block, obelisk, or temple element is a testament to the enduring legacy of ingenuity and devotion. The Egyptians transformed simple tools into monumental achievements, leaving a world that continues to challenge, educate, and inspire all who seek to understand the intersection of human knowledge, creativity, and faith. As we stand today before the monuments of ancient Egypt, the pyramids that pierce the desert sky, the obelisks that rise in silent grandeur, and the colossal statues that gaze eternally over the Nile, we are confronted not merely by stone and scale, but by the profound intelligence, observation, and creativity of a civilization that shaped human history. The story of Egyptian technology is the story of human ingenuity transformed into enduring form, where faith, science, art, and labor converge in structures that have defied the erosion of time. It is tempting to reduce these achievements to raw measurement, mechanics, or material knowledge. The Egyptians were not engineers in isolation. They were architects of culture, visionaries of devotion, and experimenters of matter. Each monument embodies not only technical skill, but also a philosophical understanding of permanence, proportion, and cosmic order. To study their technology is to study a worldview, a framework in which human action, natural law, and divine order are inseparably entwined. One cannot contemplate Egyptian technology without marveling at its scalability. The construction of the Great Pyramid of Giza, for instance, required precise planning, enormous labor organization, and a sophisticated understanding of materials and geometry. The alignment of the pyramid with the cardinal points, the internal arrangement of chambers and passageways, and the meticulous fit of millions of limestone blocks reveal a mastery of measurement and observation rarely paralleled in the ancient world. Experimental reconstructions demonstrate that such achievements were feasible with simple tools, plumb lines, leveling instruments, sledges, and a ramp, but the seamless execution over decades, often spanning multiple pharaohs' reigns, speaks to extraordinary cumulative knowledge and disciplined social organization. Beyond construction, Egyptian artisans mastered material transformation. Granite quarried from Aswan, limestone from Tura, and sandstone from Gebel Silsila were shaped, carved, and transported with extraordinary skill. Copper chisels, dolerite pounders, and abrasives were wielded with precision, producing inscriptions, reliefs, and statues of remarkable clarity and detail. Modern replication experiments have confirmed that these tools, when used with patience and understanding, could produce effects long thought impossible for a civilization without advanced metallurgy. These successes highlight that Egyptian technology was not reliant on secret, lost methods, but on acute observation, iterative refinement, and disciplined application. The ingenuity of transport remains equally remarkable. Obelisks, statues, and building blocks moved hundreds of kilometers, often across deserts and along the Nile, without mechanized vehicles. These techniques reveal not only physical insight, but logistical intelligence. The Egyptians understood load distribution, manpower coordination, seasonal timing, and resource management. Moving massive stones was a task that integrated physics, labor psychology, and environmental awareness, a multidimensional exercise of human capability. Equally impressive was the integration of celestial observation into construction. Temples and pyramids were aligned with the sun, solstices, stars, and cardinal directions, embedding cosmic significance into the very architecture. The rising of Sirius, the solstice sun illuminating temple sanctuaries, and the orientation of pyramids and obelisks illustrate a sophisticated interplay between astronomy and construction. Aligning massive stone structures with celestial phenomena required careful observation, geometric calculation, and iterative verification. A combination of practical skill and cosmological understanding rarely equaled elsewhere in the ancient world. But Egyptian technology was more than precision and scale. It was cultural expression. The act of constructing monuments was inseparable from religious devotion, political authority, and social cohesion. The endurance of Egyptian structures is another testament to technological sophistication. Pyramids, obelisks, and temples have survived millennia of environmental stress, floods, sandstorms, earthquakes, and human activity. The precision of block fitting, the quality of stone selection, and the structural ingenuity reveal knowledge of load distribution, stability, and durability. Modern engineers often marvel at the longevity of these constructions, recognizing that Egyptian architects designed for permanence. These structures are lessons in sustainability and foresight. Knowledge applied with patience, care, and intention can produce outcomes that far exceed the lifespan of individuals and civilizations. Yet, even as we reconstruct and replicate their techniques, enigmas persist. Certain methods remain partially understood. The precise logistics of moving the heaviest obelisks, the internal organization of pyramid construction teams, and the cumulative procedural knowledge preserved across generations. While modern experimental archaeology can demonstrate plausibility, it cannot fully capture the ingenuity, creativity, and situational judgment of the ancient artisans. The Egyptians' achievements are a reminder that technology is not merely a set of tools, but a living system of knowledge, experience, and adaptation. This reflection extends to the philosophical dimension of technology. Egyptian monuments are evidence that engineering is inseparable from human purpose. Knowledge alone of stone, measurement, and mechanics is insufficient without vision, discipline, and societal coordination. The Egyptians recognized that the act of building was also an act of meaning-making. To carve, move, and align was to inscribe permanence, authority, and belief into the landscape. Modern observers may admire the technical skill, but the full magnitude of the accomplishment lies in the integration of intellect, labor, culture, and spirituality. Consider the obelisks, rising as single monolithic stones, carved, transported, and erected with astonishing precision. They were more than engineering challenges. They were cosmological statements, symbolic conduits linking earth to sky, pharaoh to sun god. Their erection required the synthesis of mechanical knowledge, measurement precision, labor coordination, and religious intention. In them, technology becomes poetry, mathematics, physics, and devotion converge to produce form and meaning simultaneously. Such integration is a hallmark of Egyptian innovation, illustrating that their achievements cannot be separated from the worldview that inspired them. Similarly, pyramids exemplify the fusion of mathematics, labor, and cosmology. The Great Pyramid's internal chambers, passageways, and structural innovations reveal not only an understanding of weight distribution and stone properties, but also a symbolic architecture of life, death, and the cosmos. Alignments to stars, internal geometries, and construction sequences demonstrate the Egyptians' ability to integrate multiple layers of knowledge into coherent, enduring forms. Each stone, each chamber, is both a technical accomplishment and a narrative device, preserving the philosophical and spiritual ideals of a civilization in tangible form. Modern reconstructions further illuminate the human dimension of Egyptian technology. Teams attempting to replicate pyramid construction, obelisk erection, or stone transport experience firsthand the labor, coordination, and problem-solving involved. Such experiments reveal the cognitive and social sophistication required: task delegation, contingency planning, iterative verification, and error correction. Technology in ancient Egypt was not merely about tools. It was about people, organization, and cumulative knowledge preserved across generations. Without coordinated human effort, even the simplest mechanical insight would have failed to produce enduring monuments. Moreover, Egyptian technology teaches lessons about sustainability and adaptation. Builders relied on local materials, seasonal labor, and careful environmental observation. Water from the Nile, natural sand, and stone deposits were integrated into logistical planning. This balance of natural resources, human labor, and technical knowledge allowed monumental construction to flourish without overextending societal or environmental capacity. In this sense, Egyptian engineering was not only technically sophisticated but ecologically and socially aware, reflecting an early understanding of resource optimization. The enduring legacy of Egyptian technology extends beyond physical monuments. It resides in inspiration, in the awe these structures provoke, and in the questions they compel us to ask. Scholars, engineers, and lay observers alike continue to investigate, experiment, and hypothesize about techniques, logistics, and methods. Each reconstruction, each experiment, deepens understanding and admiration for a civilization that harmonized art, science, and faith. Ancient Egypt teaches that the greatest technological achievements are those that embody purpose, culture, and vision, enduring as both functional and symbolic structures. Finally, reflection on Egyptian technology prompts broader contemplation about human potential. If a civilization 5 millennia ago could achieve such precision, scale, and integration without modern tools, what does this imply about the power of knowledge, observation, and collective effort? Egyptian monuments remind us that technology is not merely machinery, but it is the disciplined application of understanding, imagination, and cooperation. It is a testament to the human capacity to transform vision into reality, embedding meaning into matter and leaving a legacy that transcends time. In conclusion, the technology of ancient Egypt endures as a monument not only to engineering skill, but to human creativity, vision, and devotion. Pyramids, obelisks, temples, and statues remain as testaments to a civilization that integrated observation, mathematics, materials, labor, faith, and art into achievements that continue to inspire and educate. The Egyptians mastered stone, geometry, and organization, yet they did so not for mere utility, but to embody cosmic principles, social order, and spiritual belief. Studying these monuments is to witness human ingenuity at its most profound. They are reminders that technology, when combined with vision, culture, and purpose, can produce outcomes that endure far beyond the lifespan of their creators. Ancient Egyptian technology exemplifies the timeless principle that human knowledge, applied with discipline, imagination, and collective effort, can transform landscapes, inspire generations, and leave a legacy that continues to awe, challenge, and illuminate our understanding of what it means to be human. As we leave the shadow of the pyramids and the gaze of colossal statues behind, we carry with us a renewed appreciation for the depth of human capability. Ancient Egypt teaches that true mastery is not in the tools alone, but in understanding their purpose, harnessing natural forces, and aligning action with meaning. The civilization's enduring monuments are thus more than history. They are living lessons in ingenuity, devotion, and the enduring power of knowledge applied with precision and vision.